Hello everyone, Professor Clark here in these strange times dealing with the COVID virus. Everybody is aware that the semester has been canceled, okay, or the university has been locked down. So therefore, what I'm going to try and do is I'm going to try and create several YouTube videos discussing the math that we need in order to finish out the semester, and that is most specifically rafter math. Okay, I get lots of feedback from students over the semesters that they like to see it on the board. Okay, it's everybody knows that it's easier to understand our math if we can walk through example problems on the board. So that's what I'm going to attempt to do. Okay, now all of you should have received several handouts. Okay, first off, you received this handout. Okay, you should have gotten it in an email. Okay, so I've instructed all of you to print it off and have it with you as we go through this math. Okay, and again, this handout that I gave you discusses pitch, okay, as a specific type of communication that gives us the information that we need to understand the slope of our sloped roof system. Okay, so all of you should have read that. Okay, here we have an example roof system. Okay, it's in plan view. Okay, and then it's got additional mathematical information. Our 712 pitch can tell us what our slope is, giving us the ability to understand in elevation. Our 18-inch overhang, which we'll discuss as I move forward, okay, tells us the size of our rafter and tells us our on-center spacing, 24 inches on-center spacing. Okay, gives us different spans, 14 foot, 24 feet. Okay, and again, we can understand that information and use that as our example problem as we move forward. Okay, next we have our terminology. Okay, I have my basic rafter information. I have my ridge. Okay, the ridge is at the top of our slope roof system. I've got my top plate, the top of our wall. Okay, then I've got different types of rafters. Okay, I can see that I've got common rafters right here. I've got hip rafters right here. I've got valley rafter right there. I've got jack rafters down here, and then I've got cripples, okay, which are basically jack rafters that run from one rafter to another. Okay, we are going to focus on commons, hips, and jacks. Okay, once we understand those, we can understand the additional information in this roof system. Okay, and again, what we're talking about here is not necessarily the ability to cut and build a rafter system. Okay, what's important is that we understand the math, most specifically the geometry that we deal with when we talk about a slope roof system. Okay, and we'll talk about that more as we move forward on the board. Okay, so understanding our basic terminology. And then we also understand, as we talked about in the handout that you guys had, okay, we understand that we have a total run, we have a total rise, we have a unit run, and we have a unit rise. Okay, so everybody can look at this handout that shows basically we are creating different shapes. Okay, and those shapes are triangles. Okay, and by understanding our unit run and our unit rise, we can understand the information we need to understand regarding that triangle. Okay, so again, as I start to make my drawings, I'll explain all of that more. Okay, some of the things that we've discussed in the handout, that my span, okay, is the width of my building from framing to framing. Okay, so that means from outside of 2x to outside of 2x. Okay, and my run, my total run, is always half that span. Okay, that's not true once we get to jacks, but for now, we're going to say that our run is always half my span. Okay, we're going to start out by talking about commons, then we're going to talk about hips, then we're going to talk about jacks, and when we get to jacks, we'll see some slight differences in our jacks. Okay, well, again, what are we doing here? We're trying to solve for what? The hypotenuse of that triangle. Okay, we have our span, that's the type of information that's given to us. We have our pitch. Okay, from there, we can start to understand all of the other components that we need to understand using our algebra to solve for our geometry. Okay, and as you'll see, and if you start to understand as I explain this, we're dealing with very simple shapes. We're dealing with triangles and we're dealing with squares. Okay, again, we'll talk about that more as we move forward. Okay, some additional information on here, and I will explain that as we move forward, and you can refer back to this as you need to. Okay, And then the last handout that you received is a photocopy. Okay, no fun. Again, we're not in lab, so we can't actually put our hands on it. But we have a photocopy of a framing square. Okay, again, I will talk about that more later as we move forward. Right now is just the introduction to our rafter math. Okay, so looking at that on the board, okay, again, what are we saying? We're saying that we need to be able to understand everything once again in both plan and elevation. So looking at it in elevation first, what do we see? We see our rafter. Okay. And we should be able to understand that each of those rafters, even though my sketches always leave a little bit to be desired, are what? They're exactly the same. Okay, this rafter is exactly the same as this rafter. Okay, I see my double top plate system. Okay, and again, my print gives me this span. Okay, it tells me, in our case, that span, if we use our example, okay, okay, this big rectangle is what we'll talk about, is 24 feet. Okay, so again, keep this by your side so that you can refer to it. So if our span is 24 feet, I can therefore create a triangle right here, and we understand that our span, or the bottom leg of that triangle, is half of that span. So my run there would be 12 foot, and my run there would be 12 foot. Okay, so some of the information that we need to understand. Again, this is the information that was given to me, okay, but by understanding the shapes, I can determine that information. Okay, I know my ridge is in the center. Okay, I know my span is from outside of framing to outside of framing. Therefore, I can create that triangle, and I know that my total run is 12 feet. My total run is 12 feet. I know that both of those triangles are exactly the same. And from there, they further define it for us by giving us our pitch triangle. They tell us that for every 12 inches of unit run, we have 7 inches of unit rise. Okay, so again, I have a total run, I have a unit run, which is always 12 inches. Okay, I have a total rise, and I have a unit rise. There's a direct correlation to all of those. The unit rise is directly correlated to the total rise. The unit run is directly correlated to the total run. Okay, then in addition to that, we create another triangle right here, which is our overhang. Okay, in our case, we refer back to our handout, okay, back to my print, okay, and it tells me that my overhang equals 18 inches. So now we have another triangle with a bottom leg of 18 inches. Okay, starting to solve for all of the information that we need to solve for. Okay, so again, we've created a big triangle. We understand our little triangle. We've created another triangle, and we understand our little triangle, or our unit triangle. Okay, what is our unit triangle telling us? It's telling us that for every 12 inches of run across this run, okay, I have how much rise? For every 12 inches, I have 7 inches. For every 12 inches, I have 7 inches. For every 12 inches, I have 7 inches. And on, all the way across this total run. Okay, for every 1 foot, I have 7 inches of unit rise. And how many of those unit triangles am I going to have? I am going to have 12 of them, because that is our run. So I know that I'm going to have 12 1-foot increments across this bottom leg, and each one of those 1-foot increments is going to have a rise of 7 inches. Okay, so therefore, again, I can directly correlate my unit triangle to my total triangle. Okay, so again, understand what we're talking about here. What we're talking about here is taking the information that's given to us and setting the problem up in order to solve for the information that we need. Okay, we've done it so far. Okay, we've understood that I can solve for the fact that my bottom leg of my triangle is 12 foot. Okay, either triangle, or my run is 12 foot. Okay, I understand that my unit rise is 7 inches, directly correlated to my unit run, which is 12 inches. Okay, so again, we can start to set our math problem up in order to solve for what we need to solve for. And what do we need to solve for? We need to solve for this A dimension and this B dimension. And we will get to that as we walk through example problems. Okay, you might ask, why did we break it up that way? Could I solve it from here to here? Absolutely, if I wanted to, I could. Okay, that's the whole point. We determine how to set up the math problem. Okay, if we were in school right now, if we were in the Granger building, we would set it up this way because we would cut and build this rafter. Now, we don't have the opportunity to do that, okay, but that's still how we're going to solve the math, as if we were going to do that. Okay, but if I were in the real world and I wanted to solve it from out here to here, I could do that. Is there an opportunity where I would need to do that? Yes, an estimator might need to solve that. Because is this rafter going to be 12 feet long? No, it's going to be bigger than 12 feet because it's the what? It's the hypotenuse of that triangle. Okay, so understanding that, we know that it's going to be longer. Okay, so if I were to estimate or order that material, obviously I know it's going to be longer than 12 feet, but I need to know how much longer than 12 feet. I would need to solve for that information. Okay, again, we're going to solve it this way. We're going to break it up into our A dimension and our B dimension. Okay, but the point is that I have to have the ability to set this math problem up so that I can solve for whatever it is that I need to solve for. In our case, it's that A dimension and that B dimension, but in other cases it might be that total dimension. Okay, so moving forward, that's what we're going to do. We're going to solve it in our A dimension and our B dimension. All right. All right, now looking at it in plan view, again, we have to have the ability to understand it both in plan and in elevation, just like everything we've seen so far in the entire program. Okay, I have to be able to understand it two-dimensionally in plan, two-dimensionally in elevation, which gives me the ability to understand it three-dimensionally in the real world. Okay, so looking at it in plan, we are going to take one of our shapes. We're going to take our big shape. Okay, so we're going to take this, what? Rectangle, okay, and understand it in plan. Okay, and again, what are we saying here? We're saying that that rectangle, okay, is the same as this what? Square right here. All a rectangle is an elongated square. Okay, so again, by understanding that geometry, we can use our algebra to solve for whatever we need to solve for. So I look at my rectangle, and what do I have? If I take just that rectangle separately, I have a hip roof in plan. Okay, what do I see? I've got some series of hip rafters, common rafters, and jack rafters. Okay, again, we are going to focus on our common rafter first, and our jack raft, our hip rafters next, and then our jack rafters. Okay, so what do we have here? We know this information is given to us, that I have a span of 24 foot 0 inches. I know that I have a 7/12 pitch. I have an 18-inch overhang, and each one of these rafters are placed 24 inches on center. Okay, again, that information was given to me. Okay, they gave me the information I need in order to solve for whatever else I need to solve for. Okay, again, an example of what we've seen a million times. Every time I look at a print, I see that I don't have every piece of information there that I want, but I usually have all the information there that I need to solve for whatever I want. Okay, so looking at this in plan, we understand a few things. Again, I can confidently say I can solve for the fact that if that's 24 foot from outside to outside, that's 12 feet from there to center of my ridge, and 12 feet from there to center of my ridge. Okay, again, seeing it in plan. Okay, what's the difference? This time, the shape I am seeing is a rectangle. Okay, I've got a 90-degree angle there, there, and there. Okay, again, a rectangle is just an elongated square. Okay, so what it comes down to is that when I'm looking at most shapes in the construction industry, definitely with a sloped roof system, okay, but pretty much true across the board, whether I'm talking about a floor system, a wall system, okay, a roof system, doesn't matter. For the most part, I can separate my building into squares and triangles. Okay, and we understand, like we've already pointed out, that that triangle is most of the time a right angle triangle. Okay, and often, okay, in plan, we can see that it is a 45-degree right triangle. That's 45 degrees and that's 45 degrees. In elevation, it's a pitch triangle. Okay, we could solve for that angle if we wanted to, but we don't because we don't have any reason to. Okay, the pitch defines what that slope is. Okay, so again, in plan, we understand that we've got certain shapes. We've got squares or rectangles, and we've got triangles. In elevation, we've always got a triangle. That triangle is some slope, okay, and that's our pitch. It tells us that, even though I'm looking at it in plan, it tells us right there, it defines for us what we see in elevation. We see a 7/12 pitch. For every 12 inches of horizontal run, I have 7 inches of vertical rise. Okay, again, seeing the same information over and over. Okay, so now, again, we are going to start with this common rafter. Okay, we have a common rafter there, we have a hip rafter here, and then we have a jack rafter here. Okay, so common, hip, jack. What does that mean? Okay, common rafter means that I'm hitting my top plate at 90 degrees. Okay, hip or valley tells me that I'm hitting my top plate at 45 degrees. Okay, again, when we get to jacks, there's some differences, so we'll talk about that separately, but I understand for now that I'm hitting my top plate at 90 degrees. Okay, right now we're going to look at commons, then we're going to look at hips. My common hits my top plate at 90 degrees. So I see it in plan as a rectangle or a square, and I see it in elevation as a triangle. I understand all of the information that I need to understand. I understand that this run is 12 feet from there to there. Okay, then it's going to be 18 inches from there to there. Okay, and then again, understanding that in elevation gives me the ability to solve for whatever I need to solve for. Okay, all right, so again, understanding it in plan and understanding it in elevation. All right, so again, we talked about our terminology in our handout, okay? And we said that our span, our terminology, very important to understand our terminology. Again, just like I said in the handout, terms mean something specific, and we need to understand what that specific meaning is in order to understand how to set our math problem up. So our span takes us, it's the width of our building from framing to framing. The span gives us our run. We know as long as our ridge is in the center of our roof line, which it is for our purposes, my run is going to be half my span. Okay? Then from there we understand our pitch. Okay? And that is my unit rise and unit run. Okay, my unit run is always 12 inches, and my unit rise is our definition of slope because it's some amount of rise for 12 inches of unit run. Okay, so from there we can start to understand what we need to understand. We can start to solve for what we need to solve for. All right, so going to our problem, looking at our 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 handout. Okay, we've got a 24-foot span. We've already determined that we can solve for what we need to solve for regarding that, knowing that information. Okay, so looking at one side of that rafter system, looking at one of those triangles, again, I determine that I am going to set up my problem from here to here and from there to there. Again, I am going to say that that is my A dimension and that is my B dimension. Okay, so again, I can say I've got a triangle here. I see that triangle, and I've got a triangle here. I see that triangle. Again, knowing that our span is 24 feet, 0 inches, I can solve for my total run, which is always half my span, except in the case of jacks. But for now, that's what we're going to look at. Okay, so the bottom leg of that big triangle is my total run. That's going to be 12 feet. And then the bottom leg of this triangle is going to be 18 inches because that's my overhang. Again, I determined to set it up that way, A and B. Okay, so what do we have here? My A dimension takes me from the center of my ridge, okay, to the back of my bird's mouth. My B dimension takes me from that point to the end of my overhang, the end of my tail. Okay? All right, so now, again, can we solve for that? Yes, I can solve for that understanding my pitch triangle. Okay, so my pitch triangle in this case is a 7/12. What's that telling me? Again, it's telling me that I have 7 inches of unit rise for every 12 inches of unit run. Okay, I've already discussed it. That's telling me that I've got a bunch of triangles, okay, some amount of triangles running across the length of this big triangle. And understanding that each bottom leg of those little triangles, or unit triangles, is 12 inches, okay, I can say, well, I know that I have 12 of them, okay? So from there, I understand that for each one of them, I have 7 inches of unit rise, okay? So therefore, I can solve for my A, okay? First, let's write down what we need. I need my A, I need my B, I need my C, and I need my run. Those are the things that I need to solve for. Okay, we've already solved for our run, okay, which is 12 foot, 0 inches. Okay, next we need to solve for our C. Okay, what is our C? Our C is the hypotenuse of our unit triangle. Okay, right there. 7/12 pitch. Okay, C is the hypotenuse of that unit triangle. All right, everybody should already be able to understand how to solve for that. Okay, I know that this is what? A right angle triangle. Okay, therefore, that means that I can use the Pythagorean theorem. A squared plus B squared equals C squared. Okay, do we have our A? Yes. Do we have our B? Yes. Can we solve for our C? Okay, so if A squared plus B squared equals C squared, in this case, C squared equals 7 squared plus 12 squared. Okay, so C squared equals 49 plus 144. So C equals the square root of 144 and 49. So 9, 10, 13, 9, 193. Okay, everybody go to your calculators and do that. Okay, get your calculator out. I'll give you a couple of seconds to do that. Okay, let everybody solve for it. Okay, I'm not just going to tell you. I want you to solve for it. Okay, it is 13.89. Okay, and what are my units? My units are inches per foot of run. Okay, now some of you, if you were paying attention while I told you to solve for it, if you're looking at me while I told you to solve for it, saw me look at my framing square. Okay, one thing that you guys will not be able to do because we can't go to class is that you will not be able to look at this rafter table live unless you have a framing square in front of you, okay, which you can do. You can go out and purchase a framing square if you want to, okay, or maybe your dad has one or you have one, whatever. Okay, but on most framing squares, we have what is called a rafter table. Okay, I gave you a handout, okay, made a photocopy of a framing square so that you guys could see it, okay, but if you have an actual framing square, or you can take that photocopy, okay, you can see right here that I have words at the top of my framing square, or on the side of my framing square, okay, that there's different rows, and I can see that those words carry that row all the way across. Okay, if I look at the top row, it says length of common rafters per foot of run. If I look at the next row, the second row, it says length of hip or valley rafters per foot of run. Okay, what did I read underneath? I went over to the 7 right here, and I looked underneath that column under my first row because I'm working with a common rafter. Okay, I'm determining the hypotenuse of the pitch triangle for a common rafter. I look under that, and what does it say? It says 13.89. Okay, what is that telling me? That tells me that my rafter table gives me all of the possible hypotenusae for any possible pitch triangle. Okay, so the information is right there for you. Okay, if I were in the field and actually building this, I would not need to get my calculator out if I didn't want to. Now, for your guys' sake, you have to use your calculator. Okay, because you don't have a framing square in front of you and you're not actually laying it out. Okay, but understand that. Okay, this has all been solved for me. And that is basically because the geometry we deal with in the construction industry is not that complicated as far as the different types of shapes that we deal with. Okay, so since we're dealing with a finite amount of possible pitch triangles, okay, this rafter table can be developed and give me all of the possible hypotenusae for any given pitch. Okay, so kind of cool. Okay, it's one of the things that make a framing square a very cool tool. Okay, but again, we can also solve it using our calculators just like we normally would. Okay, so that now that we've solved for that, our C is 13.89 inches. So now I can fill that in right here. 13.89 inches per foot. Okay, so again, now we can start to say, all right, if I'm going to correlate this pitch triangle to this big triangle that I'm dealing with, and eventually to this little triangle, okay, but right now we're talking about this big triangle. Now I know that I've solved for that dimension right there, 13.89 inches per foot, 13.89 inches per foot, okay? So I've got a 12-inch bottom leg on my unit triangle, I've got a 7-inch vertical leg on my unit triangle, and I've got a 13.89 inch per foot, okay, hypotenuse on my unit triangle. Okay, and again, hopefully it's making sense to you as we go through this. Okay, I know that I've got how many of those unit triangles running the length of this bottom leg. Okay, I've got 12 of them because I've got 12 feet. So if I've got 12 feet, 1 foot increments, okay, I know that I'm going to have 12 of those or 12 of those unit triangles running across the bottom of that. So therefore, our next formula, okay, and that is that A equals my C times my run. Okay, A equals C times run. Okay, what is my C? 13.89 inches per foot. What is my run? 12 foot, bottom leg of my big triangle. Okay, right there. So that times that will tell me that. Okay, I should be able to see that because I have that big triangle and I have all these little triangles, each one of them having a bottom leg of 12 inches. Okay, I've solved for the hypotenuse. If I've got 12 of those, I just have to take all 12 of those hypotenusae, add them together, or multiply the two together and solve for that A length, which is the dimension that I want. Okay, so A equals C times run. So that means I've got 13.89 inches per foot times 12 foot. Okay, I'll write that a little bit different for you. Times 12 foot. Okay, so now what happens? My feet cancel. I say 13.89 times 12. Okay, Hold on, I'll be right back. Sorry about that. Dealing with the COVID virus, just like everybody else. 13.89 times 12 gives me 166.68 what? Okay, my feet canceled, so what's left over? Inches. 166.68 inches. Okay, do I want that dimension in inches? No, of course not. I want it in what? I want it in feet in inches. So what am I going to do? 166.68 inches divided by 12 inches per foot. Okay, my inches are going to cancel. Okay, and I'm going to be in what? I'm going to be 13.89 decimal feet. Okay, so that tells me that I've got 13 feet and some increments of a foot. 0.89 increments of a foot. Now what? Now I say times 12 inches per foot. Now my feet cancel. So 0.89 times 12 gives me 10.68 what? Inches. 10.68 inches. So 13 feet, 10, and because we are Americans, I want it in fractions of an inch. So now my 0.68 times what? Times 16, because that's what our tapes read to. So 0.68 times 16 equals 11. 10.8, which rounds up to 11. Okay, so my A dimension is 13 foot, 10, and 11/16 inches. Okay, again, hopefully everybody understands the geometry, okay, the triangle, okay, both in plan and elevation, square in plan or rectangle in plan, and triangle in elevation. Okay, that gives us the ability to solve for that A dimension. Okay, how about this one? Now we need that little triangle because we still need that B dimension. Okay, everybody should be able to see it. It's going to be the same thing. Okay, I'm going to have several little triangles running across here depending on what that dimension is, what that length is. Okay, well, how many triangles am I going to have? Okay, hopefully some of you are seeing it. This dimension has to be in what? It has to be in feet, decimal feet. Okay, so I'm going to divide that by 12 inches per foot. Don't need a calculator for that because that's 1.5 feet. Okay, or 1 foot 6 inches. Okay, hopefully everybody sees that. So how many triangles do I have? I have 1.5 of them. Okay, all right. So our formula for my B so B equals C times my overhang in feet. It has to be in feet in order for my feet to cancel. Okay, it's given to me in inches. So again, one more time, I have to be able to solve for what I need to solve for. I set the math problem up. It needs to be in feet because my C is in inches per foot. Okay, I need those feet to cancel. Okay, so I need to know that I need to convert that 18 inches into feet. So 18 inches divided by 12 is 1.5. Okay, easy enough math, but you have to understand how to set it up. Okay, so again, my C, 13.89 inches, times my overhang, which was given to us. Okay, our overhang, they told us it was 18 inches. Okay, that was given to us on our print. Again, communicating information to us. So C times my overhang in feet. So therefore, 13.89 inches per foot times 1.5 feet. My feet are going to cancel. I'm going to do that math. 13.89 inches per foot times 1.5 gives me 20.835 what? Inches, because my feet canceled. That's what I wanted. Okay, so again, divide that by 12 inches per foot. Okay, that's going to put my inches are going to cancel, and that's going to put me in feet. Okay, so I divide by 12, and I have 1.736. Okay, 1.736 feet. Okay, 3 decimal places is enough, everybody. That's all the further I need to go out. Okay, so if you want to be exactly the same as me, clear your calculator and go to just 3 decimal places. Okay, so back up to here. Again, that means that I've got how many whole feet? I've got 1 whole foot. So I've got 1 foot and some increment of a foot, 0.736 feet. Okay, less than a foot. So now multiply by 12 inches per foot, okay? And that's going to put me in inches, which is what I want. So I clear my calculator, 0.736 times 12 equals 8.832 inches. Okay, again, that's what's left over. So that means I have 8 inches and I have some fractional inches, increments of an inch. Okay, and I want it in 16, so 0.832 times 16. And I get 13.3, so 13 sixteenths. Okay, so that means my overhang is 1 foot, or my tail is 1 foot 8 and 13 sixteenths. Or my B is 1 foot 8 and 13 sixteenths. Okay, so finally, we're saying that from the center of the ridge to the outside of the bird's mouth, I've got 13 foot, 10 and 11 sixteenths. Okay, and then from that point to the end of my tail, I've got 1 foot 8 and 13 sixteenths. Okay, the information I want. Okay, I've solved for what I need. Again, if I were to build that rafter, that's the information I need. If I want to know from outside to outside, I can solve for outside to outside. Okay, right now I could just add them together. Okay, or I could skip steps and just solve from outside to outside using the Pythagorean theorem, setting the entire thing up. Okay, again, we're not going to do that, so I'm not going to go through it because we're looking at it just like we would look at it as if we were going to actually build this in the lab. Okay, again, unfortunately you can't. I feel very bad about that, but there's nothing none of us can do anything about it. Okay, but that is our math. Okay, so that is my rafter math for my common. All right, so finally, to end our conversation, okay, we've got a few important aspects. My span equals the width of my building from framing to framing. My run is always half my span. My unit run always equals 12 inches. My unit rise is a function of my pitch. So some amount of rise for 12 inches of run. Okay. I solve for my A and my B. Okay. So my A equals my C times my run, and my B equals my C times my overhang in feet. Okay, so those would be the important things that we touched on today. Understanding what my pitch is doing for me, that tells me I need to take my span, determine my total run, so I can solve for that. Okay, I need to understand my pitch triangle, my amount of rise per 12 inches of unit run. Understand that that directly correlates to both this dimension and this dimension. Okay, so hopefully it's making sense. Again, ultimately, what are you learning here? Ultimately, what are we talking about? We're talking about the ability to utilize a print. You have to be able to get into the print and solve for anything that you need to solve for mathematically. Okay, again, you have to have the ability to set that math problem up. Okay, and again, We chose to look at it like we're building the rafter, so that's how we set the math problem up. But I need to have the ability to set that math problem up no matter what I need to solve for. Okay? And again, we're using the communication, the information that's being communicated to us from the design team in order to set that math problem up and solve for whatever it is that we need to solve for. Okay, in this case is our example problem. We solved for a common rafter. We determined our A dimension for that common rafter. We determined our B dimension for that common rafter with the given information, a 24-foot span, which means that we have 12 foot of run. We understood our pitch triangle. We solved for our C. We applied A equals C times run and B equals C times overhang, and we solved for those dimensions. All right, so that's it for this one. Hopefully that makes sense to everybody. What's important is understanding the geometry, understanding how to set up the problem to solve, use our algebra to solve for that geometry, and do what we need to do, solve for what we need to solve for. Okay, so that was our common rafter. I am now going to make another video that is going to show you how to solve for your hip rafter. All right, thanks. That's it.